This video will demonstrate the use of the Symmetry-Adapted Perturbation Theory program within Psi4. So I'm inside the Avogadro molecule editor here, and I've drawn these two benzene molecules in a dimer, and that's kind of a tilt T-shaped benzene dimer. And I want to compute the interaction energy between these two molecules. So I can do that and get a sense of how strongly these benzene molecules either attract or repel each other in this particular configuration. But let's say I also want to know more than that. I want to know what's the physical origin of the interaction between these two molecules. Is it electrostatic between the hydrogens pointing down towards this ring centroid, kind of a partial positive, partial negative thing? Or is there some big steric clash, some exchange interaction that I have at this configuration? Is there a whole lot of induction or polarization going on? Or is this interaction primarily due to London dispersion forces? So Symmetry-Adapted Perturbation Theory, or SAPT, or SAPT, is a method which can answer those kinds of questions and give you those values. So inside of, if you're in the correct version of Avogadro, I can go up to the Extensions tab, and I can select Psi4. And the default input file that it's going to give me here is a single point energy for Sap Zero, which is the 0th order Symmetry-Adapted Perturbation Theory. And the basis set that it recommends is jun-cc-pVDZ. So that's a truncated double zeta Dunning set. That's just a basis set which happens to work very well in terms of getting accurate energies with this particular SAPT method. And that's the basis set that we recommend you use with Sap Zero, which is the fast, quick, qualitative estimate of these interactions. Okay, so I've got that input file there. It sets my basis set, declares my molecule, gives me Cartesian coordinates, and gives me the energy method. So if I take that, and then I have essentially that in this demo7.in input file. So it says for memory 2000 megabytes, same thing, molecule, and energy Sap Zero for my computation. So normally what I would have to do in order to do this calculation is that I have benzene molecule number 1, which I've declared as a neutral singlet, and I would have to do dash dash, new line, neutral singlet for benzene molecule number 2. And then Psi4 would recognize that this is monomer A, this first benzene, and this is monomer B, the second benzene. But the great thing about Psi4 is that there are multiple ways of doing things, so I don't even have to know that necessarily, as long as I'm confident that I've got two molecular fragments, which is what I need for SAPT, because I need two fragments a priori, because it's the way the algorithm works. So as long as I'm confident I've got two fragments, then I can call this function called autofragments, and Psi4 will go through and try to figure out what the two fragments are for this particular computation. And these benzenes are far enough apart, being non-covalently interacting, that it's going to correctly determine which is which and have our two monomers that we need. Okay, so I'm going to run Psi4 for this demo7.in. I can give it an output file name if I like, running in background. Let's do that with 4 threads. Okay, I'm going to tail my output file. So the first thing that it's going to do is run an Scf calculation on the dimer. So this is both benzenes at the same time. And that'll converge to a final value. It's going to run an SCF on monomer A, one of the benzenes, in the basis set of the dimer. So it'll have ghost functions on the other one. Then it'll run the SCF for monomer B, same thing for the other monomer, running in the dimer basis set with ghost functions. Now it's going to run a Sap Zero calculation. So the first thing it's going to do is compute the electrostatic interaction between the two molecules. Then once that's done, it'll compute the exchange or the steric interaction, and there are those two. Now it's going to do two coupled perturbed Hartree-Fock calculations to get the induction or the polarization. And then it's going to compute the dispersion, the London dispersion forces, and other components called exchange dispersion, and then summarize those results, and we're going to leave. So Psi4 exiting successfully. Our output file has finished and didn't have errors. So now I'm going to go inside of our output and check that out. was all the things I just discussed as they came up on the terminal. But the nice thing that we have at the end is the summary of the SAPT results. So what we have here is a final summary of the electrostatics being minus 0.87, or attractive by about 0.9 kcal per mole, kilocalories per mole. The exchange being repulsive, the repulsive steric interaction of about 1.1 kcal per mole. Induction being attractive by a slight amount, 0.2. But the big interaction we can see here is from dispersion, the London dispersion forces, as you would expect from such a big kind of molecule with such diffuse pi clouds interacting. You're getting the correlation between all those electrons. So summary of dispersion being the dominant term there. Then, as we can see at Hartree-Fock, it's unbound, as these systems typically are that have a high amount of correlation energy. And then we have our total Sap Zero interaction energy as sum of those four terms. And we get minus 2.3 kcal per mole. So now I've got a lot more insight into this system. I know that this interaction has a little bit of favorable electrostatics that are pretty much canceled out by the exchange interactions, but that the dominant component that's coming into play here are the London dispersion forces. So that's the basics of the SAPT program within Psi4.